look at this instruction website. Do you know where this is, right? Okay, good. And then, so instruction about presentations are here. And then if you go to this sign up sheet, then, okay. So people sign up. So is there any one of you guys in a group 1 here today? You group 1? Okay. So what's the name? Norris. Morris. Okay, good. So yeah, please prepare. You okay? September 23rd. You guys are the first one. Yeah. So first one may be a little more difficult, but then so if you have questions, you can ask them. Yeah, please prepare. Start preparing in advance. And then okay. There are a lot of people sign up. This is good. So Morris, did you find the anime? Not yet? Doraemon? Okay, yeah, good. Actually, if you present earlier, it's easier to find a topic or anime, right? If you're in December, maybe a lot of anime is already presented by other people. That could happen. Is there anyone in December 12th? What's your name? Martin? Martin here? Okay. So, was fine. Yeah. So, Martin, when you pick an anime, please make sure that please check the previous people, what they presented. Yeah. Okay. And then for Martin, this group, the report deadline is only 3 days, right?
No, because the presentation is December 12th, so we still have time.
We still have time?
Yeah.
When is the deadline of the report?
On the last day, because the last day is December 19th. So
okay, good.
We have 1 week to finish the report.
Okay, good for Martin. Okay, very good scheduling by Terry. By the way, Terry, but there are 4 more people sign up this morning. I look at the school system and there are 4 more people.
Then some group may increase the people to 8.
Okay, but there is no slot anymore, no open slot anymore? Because I see all of them filled, right?
I think some group has only 6 people.
Okay.
Yes.
Like here? But this...
They already put student ID.
So this person doesn't have a name?
I will send a reminder to...
Okay. Here, for example, is anyone from group 14? Is anyone in group 14? No? Okay. But if new student want to join your group, please don't reject. If someone asks you, I want to join this group, don't say no. Please, make a new friend. Okay? This group too, right? Is anyone from group 15? No? Okay. Okay, how about group 22? Anyone group 22? No? No? Okay. But I'm a little bit worried there may not be enough spot because this morning there are 4 people sign up.
Then some group may have 8 people. I think it's still okay.
Okay. How about the lady? Did you sign up? Not yet, right? Okay, you can. Okay, so can you join some group later? Yeah.
Go to EE class.
Then there's a link. Yeah. What's the name? Your name? You don't have a name? You forgot your name? No? You can look at your student ID and then that says your name. Janice? GU? GU? Okay, welcome. So if GU want to join your group, just welcome her, okay? Don't reject. Okay, good. Okay, then let's go to the lecture. Then I need to share it again. This one. Okay. All right, so let's get started. Have you heard of the Coulomb's law? I'm a little bit worried maybe everybody heard about Coulomb's. Who has never heard about Coulomb's law? So everybody knows that, right? Okay, then maybe it's easy to today, but then it's just a warm up. I need to put here. Okay. 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 Yeah, electronic charges has plus and minus, positive and negative. Maybe people know that. Does this work? What did I do? I don't know. Okay, I'm supposed to do this. Okay. Then electronic charge is conserved. These charges, plus or minus, they don't disappear suddenly. So that's good. Net charges are always constant, and then charged particle may be created or destroyed in pairs. So if plus is created, there will be minus, so that net charge is always constant. Then SI, international unit of the charge, is Coulomb C, which is 6.25 times 10 to the 18 elementary charges. Sometimes we see E. Okay, so then, okay, E, okay. 1 Coulomb is 6.225 times 10 to the 18 E, right? Then 1 E is how many Coulomb? Martin. How many Coulomb? About approximately. You don't need the exact number. Have you learned division? 1 divided by this number. Maybe you have. What's the number?
1.6 times
10 to the minus
19.
Okay, thank you very much. Very good. What's your name?
Angus.
Angus.
Yeah.
Angus. Like a steak.
Yeah.
Oh, okay, good. Angus.
It is coincidence.
Okay. Very good name. Very good. Thank you very much. Coulomb's non-electric force. The same, the like charges repel. That means, plus and then plus repel. And then minus and minus also repel. And then the opposite charges, plus and minus, attract, right? Plus and minus attract, right? Then this force depends on this. This is actually Coulomb's law. So the force, the strength of the force depends on the product of the two charges. So Q1 and Q2. So how many coulombs here, how many coulombs here. Then also depends on inverse square of the distance between them. So this R square, R is the distance between two charges. Okay, I already talked about, but say this charge is Q1, this charge is Q2, and distance is R, then force is something like this. This is Coulomb's law. And then K is a constant, and then that's the number is given there, 9 times 10 to the 9 in this unit, and R is the unit vector, so it's pointing the vector, showing the direction. And it's the same for repelling and then attracting force. They both use Coulomb's law. If plus plus, they repel each other with this kind of force. And then if it's plus and minus, then they attract each other like this with this kind of force. Okay. As you can see, this is R square, proportional to the inverse of the R square. So the force becomes quickly smaller when two charges are more separated. And then force is very strong when two charges are very close to each other. Okay, nothing difficult. Then superposition principle. If the electronic force obeys the superposition principle, meaning that if there's multiple charges like Q1, Q2, Q3, well, okay, let's see the force on Q3, and then if there's another charge, Q1 plus, and then Q2, negative charge, and then the net force is just a superposition of these two forces. This is the force from Q1, like this is plus and plus, so it repels, right? And then this is a force from Q2 because this is negative, so it's attracted. And the net force is superposition of this and then this, so that the net force is in this direction with this kind of strength. Okay, so it's straightforward. We can mathematically add the vector to calculate the force. Okay, electronic field. Electronic field, we can define the electronic field. Electronic field is the force in that particular position that is excelled by the per unit charge, if just 1 Coulomb. Okay, so you can actually divide the force by Q and then you get electronic field. Example is here. So, well, okay, the force. So this is convenient because if when you change the Q, then you can just multiply QE and then calculate the force. Okay, so I don't know. Well, so here's a plus charge, and the electronic field you can calculate it everywhere. So it's the amount of the force. You put a unit charge, say electron. If you put electron, then what force electron is going to feel? That is going to be the E, electronic field. And then you can write it in that kind of electronic field lines. And as you can see, okay, I think it's the next page. The electron field is analogous to the gravitational field, which gives the force per unit mass. We have a gravity on the Earth, right? So wherever we are on the Earth, or wherever, then we feel the gravity, right? And then the gravity, this force depends on your body weight, right? What's your body weight?
80, yeah, 80.
80, then you feel more force, stronger force than me. Okay, so, okay, and it's similar to electronic field. If you have electronic field and if you have charges more, you feel stronger force, right? So there's similarity. Then field of point charges and charge distributions. The field of point charge is radial, so outward for positive charge and inward for negative charge. If you have so let's think about in this case point charge. Say if there's an electron -1 here, then the field is going inside into that charge, and then electronic field can be written from the Coulomb's law. So this is Coulomb's law, right? And then Q1 here is 1, just 1. So it's just 1. Then another Q is just remaining. So the electronic field is something like this. Then as you can see, it gets quickly weaker with distance inversely proportional to the distance squared. So as you go farther away, electronic field gets weaker and weaker and weaker. Then superposition principle always works. So if you have multiple charges, multiple point charges, you can just sum up the electronic field and then you get the net electronic field. So for example, you have multiple charges, plus, minus, and then you want to calculate the E, electronic field of particular place, then you can just sum up the electronic field from all the other charges, then you get the electronic field of that place. Okay, then next is dipole. This is plus and minus. So electronic dipole is 2-point charges of equal magnitude but opposite signs. So something like this. There's a plus and a minus and then very close to each other. That's something called electronic dipole. And in reality, dipole happens very often. So we see this dipole everywhere. For example, water molecule H2O is also a dipole because okay, in reality this like this, but then it's similar to plus and minus, right? With the equal amount, opposite sign. So electronic water molecule is a dipole. You can consider it's a dipole. Dipole is electronically neutral because 2 plus and 2 minus, it's plus minus 0, right? Net. But the separation of its charges result in the electronic field. So because these are a little bit separated, right? Plus and minus are a little bit separated. So it creates an electronic field. Yeah. Many charge distributions, especially molecules, behave like electronic dipoles. The product of the charge and separation is the electronic dipole moment. There's something called dipole moment. This is convenient for calculation of things. Which is P is Q, amount of charges and then distance. This is something called electronic dipole. Yeah. Okay. I think we are going to calculate this soon. Okay, let's look at this example. Maybe I should put camera to me. Okay. Okay. Say there's a plus charge here and a minus charge here, and then suppose A is very small. They're very close to each other. Then this is dipole, right? Then say if you want to calculate look at the electronic field here, then why this is is there a way to change this? I think there is, right? I need to go to PowerPoint, which is here. Okay, I think, is it this one? A low option, is it this one? Okay, last build. I don't know how to change this. Maybe I don't see the option to change this. Okay, so we need to live with this. Oh, okay. So okay, fine. So the superposition principle also works, right? So from this plus charge, you get electronic field like this. From this minus charge, you get electronic field like this. So then superposition principle works, so we just add up these two and then you get electronic field like this. So dipole's electronic field goes like this, or this, from plus to minus. Okay. I think I have a figure later. Okay, then what about, so we're talking about point charges, like proton or electron, these particles. But what if it's a continuous charge, something like this? For example, human, if I'm charged, I'm continuous, right? I'm not the point. Then superposition principle also works. But in this case, just addition becomes integral. So say if this is charged object, and then if each part of this object is charged, then you can just integrate this charge over the object, and then you get the electronic field from this object. This is like, you have so many point charges. It's the same. It's always happen, right? You start with the addition and then it becomes integral. So that's it. Okay, here. Okay, now the fun part starts. Okay, so I want you to try this. This is an example. Say you have a ring, okay? A ring is charged, okay? Total charge is large Q, okay? And then there's a point P here. The distance from the ring is x, okay? And then the ring's radius is a, small a. Then question is, what's the electronic field here in P, at P? Okay. Can you try to calculate? Do you guys have a pen and paper? Or you guys just write on your iPad? That's fine. Okay. Don't look at here. This is the answer, so don't look at here, okay? Please try first yourself, okay? You need to go? Okay, no problem, no problem. Please make sure to sign up. Yeah. Okay, then while you are doing, I try to fix this pointer program. No. I fixed the problem. Good. Okay. Anyone finished? Do you need more time or someone finished? Did you finish?
Yes.
Angus, can you try to explain here? If you come up front, you get 1 point.
1 point.
Yes, even if you fail.
Upside up question.
Yeah.
Oh.
Just one. Can you come here? Who wants to hear Angus' explanation? Okay, good. Good. Thank you, Angus. Oh, this is a little difficult. Yes, okay. 자요.
Okay, I try my best.
Yeah.
First, we can calculate the the 1 point.
Sorry, can you use this?
Okay. Yeah. Also,
Put it here.
put on my coat. Okay. So this is the 1 point, and this is 1 point. So the DQ use column law. So the distance of these 2 points is x to 2 and plus a to 2, little a to 2, right. And the root. And the upside is k times dq. This is it. But we have a ring of this, so we have sum all of the point. So we have to sum all of the point. Okay, so we find. So this is the sum of the electric field.
Yes.
So this is the sum of the electric field, but we still have to count the final field. So this is theta, and the cosine theta is root. This is 2. X to 2 plus little a to 2, and this is little a. So after calculate, we can find the answer. 3. And this sum, every point of Q is the electric of the ring, and times little a. This is answer.
Yeah. Very good.
Okay, thank you everyone.
Any questions, Angus? Okay, I need to get that. Okay. Thank you. Is everything clear? Did you understand? This part is cosine, okay? So because that without cosine it's this way, right? But then because this y direction around the ring is going to cancel out, right? This way all cancel, right? Because it's 380 degrees. So only this part remains. So you need to, he's already only calculating this cosine of this there. Okay? Any question? You okay? What's your name? You forgot your name? Eileen, is it okay? Yeah. Okay, good. Okay, good. Thank you, Angus. So can you get the...
If this is cosine, so it should be x, not a.
I'm sorry. Eh?
So cosine is x divided by r, right?
Yeah.
It's not a divided by r.
Oh, yeah. So this should be x, no?
Yeah.
Oh, thank you.
Yes.
Thank you. Oh, you get the 1 point. Congratulations. Oh, thank you. Yeah. So Angus, this should be A. Oh, sorry, I didn't notice. This should be X, right?
Yes.
So now, Ellen, you said it's okay, but it was not okay. It was a trap by Angus. Okay, thank you, Darian. Oh, it's good to have good TA. Thank you. Yeah, I don't know why, but the Darian is very good at physics. Physics only. I don't know why, but he's very smart on physics. Okay, good, thank you. Okay, now shall we try this one? So can anyone try this? Did you finish this one? Not yet? Did you finish? What of you look finished? No?
No.
Okay, can you try? Come up.
No.
No one's finished? Did you finish? Oh.
I didn't try it.
You didn't try? Okay. Can you try?
Sure.
Okay. Yeah. Okay. Good. Thank you. What's your name?
You can call me Emerson.
Anderson. Emerson.
Yeah.
Okay. Emerson. Let's welcome Emerson. Yes. Good. You can just erase Angus. So now there's a line, cable, like this kind of cable, right? Cable. I have a power cable, right? And then there's it's charged delta Q. And then there's a density. Density is lambda coulomb per meter. And then what's the electric field here? That Emerson is going to try. Darian, did you find Angus in the list? Can you put 1 point for Angus? Yes.
I will assume these two theta.
Yeah.
And cosine theta will be this.
Okay.
Okay. And
Oh, I'm sorry. Can you use this one? It's already
okay. Let me assume this point to point A, and this will be point B.
okay.
And the charge on point A will be dq if the total charge will be big Q. So the point A's electron field will be will be okay, and the electrified to points P from points B will be like
Yes?
and the vector of A and B will
X
to
direction, yeah.
0 in the X section,
That's right.
but
Cancel out.
they only have Y sections.
That's right.
So we can, so the total electrified on the points P will be like this.
That's right.
So let's write it. So this will be the answer.
Very nice, very nice. Oh. However, Emerson, it's not just A and B. There are charges here, 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 everywhere.
Oh,
So,
so we.
Can you make it an integral?
So we need to. Sorry, I'm kind of nervous.
No problem, no problem. I mean, my class is easy, so you can just relax.
Thank you.
Yeah. Well, there's a secret. As long as you make presentation, no one fails. So just relax. Okay. I want you to enjoy the physics. Okay. Enjoy the class. That's the important thing. Yep. Okay.
That's
It looks
the
very,
final
very
answer.
good, but the little correction. So you don't need this two because it's all the way, not just here and here. It's all the way from here to here.
Oh,
So
sure.
So this is actually not A to B, but this is minus infinite to plus infinite, all the way. And then this integral, actually cosine theta is, what is cosine theta? Can you write it?
Cosine theta
It's
is
here, right? And then this integral is about x, right? Because x is from here to here. So
sure.
actually this is not just q, because this part and then this part has x. This here has x. So you need to integrate this. So x square plus y square, right? And then this is 1, right? So here, this is 3, 2. And then, well, q is fine. I'm sorry, q is fine. Q is fine. But then you need integral of this. Right?
You
you see?
mean this one?
Yeah, because x is here, right? So this value is changing as x changes.
Oh,
So
I got
you
it.
need to actually calculate this. But then that is a little difficult. Can anyone do integration of this? X square plus y square and then 3, 2. It's a little difficult, so you don't need to do it. I have an answer here. Okay?
Sure.
Okay. Thank you, Emerson.
Thank you.
Please get additional point. So, Darian, could you give him an additional score? Okay. Then let me continue. So actually that integral is a little difficult. So this is what I was talking about. So you need an integral, but then I think it's a little difficult. So you need to look at the integral table. This is the answer. This is not simple. So you need to, if you look at the table, then this is integral, and then you put that in, then you get this answer. Okay, here, okay, I fixed this. So, why? Okay, here I go, here. So here's that, right? That is here, right? And then you need integral of this. So you look at the table, and then you put table, it tells you this, right? And then you put the number, and then it's going to be like this. If you put, see, this is plus infinite to minus infinite, and then yes, you get this, and then this is the answer. This is just a calculation. So what Emerson did, equation is okay, and then if you calculate, you get this answer, this one, right? Okay, and then did you notice that this y is now it's inversely proportional, not inverse square? You remember Coulomb's law, when it has a point charge, then this was square, right? But then now, because it's a line, you have contribution to every area. Now it's not square, and then it's just inverse. So it doesn't get so weak. That's understandable, right? Because there are many more charges than a point charge. Okay? Okay? Elena, is it okay? There's no trap? Okay. Okay, so let's continue. Thank you, Emerson and Angus. Okay, let's continue. So, electronic field. Can I finish? Am I doing okay? I am not sure. Matter in electronic field. So, for a point charge Q in an electronic field E, Newton's law, an electronic force combined give acceleration, because if you get a force, so if you have point charge in electronic field, then the charge, you feel the force, right? And then it's from Newton's law, force divided by mass is you get the acceleration, because you feel the force, right? You push, so you move. If it's a point charge, that's like, and if it's a dipole, something like this, you remember dipole is plus and minus, right? Then electronic field experiences a torque. So that tends to align the dipole moment with the field. And then torque is, tau is calculated P cross E. So say if it's a plus and a minus here, dipole here, and the electronic field is this way, right? Say for example. Then this plus is going to feel the force this way, minus is going to feel the force this way. So this dipole try to rotate like this, right? Rotate in a direction of electronic field. And then that is torque, it's here. Okay, and this P is a dipole moment that we calculate, like a Q times distance, that's dipole moment. If the field is not uniform, the dipole also experiences a net force. Like for example, if electronic field here, E2, is stronger than E1, then you feel this plus feels this force, minus feels weaker force, so there's a net force. So dipole is going to move, not just rotate, it's going to move. So then dipole in an electronic field has a torque, right? So that means it has a potential energy of U equals dipole moment times E. So this is a potential energy of this rotation. Okay? Conductors, insulators, and dielectronic. So just start with the words. Materials in which charge is free to move is conductors. So like metals, like cables or irons, these are here. These metals charges can move freely, right? That's conductors. And then something charges cannot move is insulators. Like for example, rubber or woods, then they don't, the charges cannot move in the rubber or woods. These are called insulators. Okay, then insulators generally contain molecular dipole which experience torques and forces in electronic fields. Like such materials are called dielectrics. So, for example, like if something, say wood, contains water molecule, that's dipole, right? Even if molecules aren't intrinsically dipole, they acquire induced dipole moments as a result of electronic forces stretching molecule. Alignment of molecular dipoles reduces external active here. So, for example, even if it's not a dipole, so this, I don't know which molecule is this. Is that helium? Maybe helium? Oh no, because there are 4 electrons, so maybe beryllium. Okay, whatever. Say if beryllium is put in an electronic force, then these charges going to feel a little bit of force, right? So the plus is shifted a little bit compared to electrons. Then it looks like a dipole, right? So these are called induced dipole moments. Then say this is some material and then electronic field appeared, and inside the molecule the plus and minus shifts a little bit. Then there's an induced dipole. And then because when it is shifted plus and minus, there's an electric field from here. So that's going to reduce the applied electric field a little bit. So that's what happens. Okay, oh good, summary. So we learned here Coulomb's force and then superposition principle. We could just add up forces, and then we talk about electronic field, and then we calculate these charges. Emerson charge, calculate this electronic field from the line, and then okay. Now that's the summary. Okay, now we are going to play a game here. This is your favorite part. So let me prepare this. How do I do this? I need some volunteer to play game. Who is good at game? If you succeed, I give you 1 point. How do I do this? I need to go to PowerPoint to copy, right? Where is PowerPoint? Here. No. Okay, here. I copy this, and then I go here, 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 here. I hope this works. Okay, I need some volunteer. How do I share a window? No, top. This one. Do you see it? It's still playing PowerPoint. I need to finish the PowerPoint. Okay. Now you can see it, right? Okay. Okay. Who wants to volunteer? If you volunteer, you get 1 point, even if you fail. Okay, please come here. And then use this mouse, please. Okay, so there are a bunch of plus and charges. Here's a plus charge, right? And then you have these plus and minus charges, and then you put it somewhere, and just wherever you want. And then when you click start, it starts moving, and then this charge is going to feel the force from these charges, right? And then what the goal is to put this in here in the goal. Okay? So can you try to put these somewhere so that when we click start, it becomes here? Okay?
Gravity.
No gravity. This electronic field, electronic force. Yeah. Do you remember we were learning about electronic forces today? Not gravity. We'll do it in a later semester. The mouse is not working.
You need to open the website because you open the Google Meet, then you can go.
Oh, sorry. Can you click here? This tab.
This one?
No, that one. Yeah.
This one?
Yes. Don't close it. Yes, that one. Yeah.
So,
And then you should be able to. Can you? Oh, yes. What's the name, by the way?
oh, my name is Bill.
Bill.
Yeah.
Okay, Jay or Bill. You guys can give Bill hints. You can say, oh, no, there. No, it's up, down. So you can just help him. Okay, are you ready, Bill? Can you finish it in 1 minute?
The mouse is very sensitive.
You think that's okay? Do you think that works? You think that works? Okay, you have 30 seconds to finish.
Okay.
You think okay? Are you ready?
Let's try.
3, 2, 1. Yes!
Yes.
Oh, wait, is this success or not?
Collision.
Oh, okay, I think it's success. Okay, good job. Good job, Bill. Okay, now next level. Who wants to go next level? Who wants to try? How do I go to next level? Well, okay, you didn't clear, no? Because it should go to next level, no? Okay. Any volunteer? Okay, okay. Level 2, right? Is this level 1? Okay. Now, who wants to do this? Okay, reset. Okay. Who wants to try this? Okay, go ahead. So, what was her name again? Stephanie, right? Okay, good. Stephanie, Jayo. Now you see a wall here, right? So you need to go this way or this way. Okay? Jayo. Can you finish it like in 2 minutes? Because there's level 3 too.
Give it a try.
Yeah. You guys can help Stephanie.
Would this hanging from here to here touch the wall?
I am not sure. Probably it's better not to touch the wall, I think. So you need to go here, like this.
Oh. It cannot move.
You cannot move. You get clear if you want. You can.
It didn't work.
Huh? Really? Did you click?
This one?
Eh? Why? Am I in a here, right? Why it doesn't work? Maybe I should reload. Sorry, I don't know why. You are level 2, right? Okay.
Level 1.
Level 1. Okay, good. Also, Bill was practice. Sorry, Stephanie, can you finish in 1 minute? Because I want someone to try level 3. And then Stephanie, you need to go this way. So, yeah. Let's put minus somewhere. And then you need to go like this, right? So,
Maybe.
do you think this is okay? Are you ready?
Yeah.
Okay, 3, 2, 1. Oh! That was so close. You're almost there. You went here. Oh, good. Okay. Well, thank you, Stephanie. It was very close. Good. It came back? Okay. We still have 4 minutes. Who wants to try level 3? Come here. What's the name?
My name is James.
James. Jayo. Level 3. You go. Jayo. Or you want to go level 2? Okay, everybody please help James. This is a little difficult. Okay, so you go that way. This is very difficult, no? So Bill and Stephanie and James, after the class, please stop by here to get your point. You found Angus and Emerson, right? Okay. James, why don't I give you 3 chances? Because it looks impossible to succeed at the first time. I think you need it here, back of the goal, no? Because if you have it here, it comes here, and it's after this, passing this point, it's going to be a break, right? So maybe you need it somewhere here.
I will make a wall here.
Whoa! Oh, so it doesn't go? Oh, that's a good idea. Yeah, just make a wall here so that it cannot go anywhere else but here. The question is, can it get there or not? You need to pass here and here. Okay, James, we have only 1 minute, so okay, 3, 2, 1, go. James, you immediately wait. Okay, one more time. Okay, can you? Yeah, move. You need to move. Yeah. Something like that. Yeah. Okay, I think that's better. 3, 2, 1. Oh. This minus is too strong, no? Just remove this. Oh, you put the wall here. Plus wall. Any idea? Okay, it's time to finish. So this is last chance, James. It's already 9:50. We need to finish. Okay. Well, thank you, James. Okay, so it's time. So we stop here. Again, so next week I'll be at the conference. So we have no lecture. Okay, next time this September 12th, right? 12th, but then I'm still at the observatory, so I will teach online. So please join online, okay? 16th. So please join online. Then for the presentation, presentation is a big part of your score. So please start preparing early, okay? Okay, so if you have any questions? Yes, Stephanie?
Does everyone in the same group have to choose the same enemy?
That's the principle. If possible, can you choose?
Choose the same part of the enemy.
No, different part of the same film. Yeah, that would be better. Yeah. Okay.